Ever wondered how you could merge millions of groups of things together and still check if any two are connected in, like, almost no time at all? Well, that's not some fantasy. It's the absolute magic of the union-find data structure. And today, we're going to break down exactly how it pulls it off.
So this is the big problem we're tackling. Imagine you're running a huge social network, or maybe mapping out a massive computer circuit. You need to know, right now, if 2 points are connected, even if it's through a long, winding path. How on earth do you do that efficiently when new connections are being made all the time?
All right, let's dive into Section 1, the connectivity puzzle. We're going to start with the fundamental building blocks of this whole thing.
So, the formal name for this is a disjoint set union, or DSU for short. Its entire job, its whole reason for being, is to manage a bunch of sets that have 0 members in common. Think of it like a really organized manager for a bunch of separate clubs or teams.
Okay, the best way, and I mean the best way, to visualize this is to picture a forest. Seriously, every single tree in that forest is one of our separate groups. Every person or item is just a node in one of those trees. And here's the key. If you're in the same tree, you're in the same group. Simple as that. And this whole structure really only does 2 main things. First, there's find. That's where you point to any node and just ask, hey, which group are you in? The answer is always going to be the root of that node's tree. And second, there's union. This is where you grab 2 elements from different trees and merge their entire groups into one big happy tree. That's the whole shebang.
Okay, moving on to Section 2, managing a forest of sets. Let's see how this actually works in the real world. We'll start with a simple approach that, well, you're about to see has a major flaw.
So how do you actually find the root of a tree? It's pretty much exactly what you'd think. You start at whatever node you're interested in, and you just climb. You go to its parent, then its parent's parent, and you just keep following that chain up until you hit a node that points to itself. That's the root. It's the ultimate boss of that entire set.
Yep, that's the core of it. The find operation is really just a journey from a child up to its parent, and so on, all the way to the top.
But here's the catch. This is where things can go horribly wrong. What happens if, through a series of unions, you don't build a nice, bushy tree? What if you accidentally create a tall, pathetic-looking chain? You know, like a conga line instead of a real tree.
And if your tree is just one long chain of n nodes, finding the root from the very bottom means you have to visit every single node on the way up. That's a linear time operation, or O of n. And when you're dealing with millions of items, that's just disastrously slow. It completely defeats the whole purpose of using this thing.
Which brings us to Section 3, the path compression shortcut. Okay, this is where the real genius of union find comes in. To fix our sad little conga line problem, we're going to introduce an incredibly elegant, game-changing trick.
This amazing shortcut is called path compression, and the idea is just so clever. The very first time you make that long trip up to the root, you do one tiny bit of extra work. As you go, you tell every single node you visited to stop pointing to its old parent and instead point directly to the root you just found.
And just look at the difference here. On the left, that's our slow, sad chain. But after just one find operation with path compression, bam, look at the right. The whole structure just flattens out. Every one of those nodes now has a direct, first-class ticket to the root. Future searches from any of them will be instantaneous. But path compression doesn't work alone. It's got a partner in crime, you could say. It's an equally important trick that works proactively to stop those tall trees from ever forming in the first place.
This is union by size, and it's just a simple rule for our union operation. When you're merging 2 trees, don't just do it randomly. Always check which tree is bigger, which one has more nodes, and then make the smaller tree's root point to the bigger tree's root. It's just common sense, right? And it helps keep our trees short and bushy.
So here's the crucial part. What happens when you put them together? Well, look at this table. If you only use union by size, you get a pretty good OM log n time. But when you combine it with path compression, the complexity becomes O of m alpha of n. And that is just unbelievably fast.
Now, I know what you might be thinking. You see that weird alpha symbol, alpha n, and you're getting nervous. Don't be. All you need to know about this thing, it's called the inverse Ackermann function, is that it grows so ridiculously slowly that for any number of items you could possibly fit into the known universe, its value will not get past 4. Seriously. So for all practical purposes,
This is a constant. Your operations are almost instantaneous on average. All right, last section, Section 4, Mastering Union Find and Practice. Now that we have the theory down pat, let's talk about where you'll actually use this in the real world and what you absolutely need to remember for that next coding interview.
The applications for this are everywhere, especially in graph algorithms. Take Kruskal's algorithm, for example. You're trying to build a network, like connecting cities with roads, and you can't create any loops or cycles. Union Find is perfect for this. Before you add a new road, you just find if the two cities are already in the same group. If they are, adding that road would create a cycle, so you just skip it. It's that easy. It's also used for counting connected parts of a network, in computer vision, and a ton more.
So here it is, your interview cheat sheet. Number 1. Always mention both path compression and union by size. They're a team. Number 2, confidently say the time complexity is O of alpha of n, and then explain what that actually means, that it's practically constant time. 3, a real pro tip is to mention you'd implement find iteratively to avoid stack overflow problems on huge chains. And 4, know its main weakness. It's not designed to handle deleting connections efficiently.
So you see, Union Find isn't just another data structure, it's a fundamental tool for understanding how things are connected. It gives you this incredible power to model and ask questions about huge, dynamic relationships at breathtaking speed. So the only real question left is, now that you have this tool, what will you build with it?